Okay, you can get started whenever you are ready.
So, good morning, everyone. We are Group 4. So today our group will present the second progress report for the ORIPAC project. In the previous stage, we selected the ORIPAC as our final project idea because traditional backpacks often make items difficult to see, access, and organize. So in this report, we will explain how we continue the development process after the midterm. First, we summarize the customer needs and establish target specifications. Then we generated different product concepts and elevated them through a scoring matrix. And after that, we use 8OQ to connect customer needs with technical requirements and support the financial specification setting. So the first one will be presented by Hayden.
Morning, Professor and everyone. Good morning, Professor and everyone. Today, I would like to present on behalf of the team of the process of analysis and selecting the design concept, the ORIPAC Smart Backpack project. Through the process of customer research, we have established four must-have. The first one is dedicated laptop rotation. The second one is the ultra fast transition. The third one is the quick access pocket, and the fourth one is adjustable opening level. Nice to have is the ultra lightweight design and water resistant outer fabric. The next one, please. And yeah, and based on the customer research, we are established the tariff specification. I said before we have four must have, including fast, accessible, protective, and adjustable. And customer about the fast customer need time to fold and unfold the backpack and minimal the steps to transform and open. And we aim to correct the thing under 5 seconds. And the second one is acceptable. We need the customer needs wipe, fill, and view to the organize and take the most item. About the engineer metric, the surface area is both when the fully open. The score either 4 and rotate to the customer needs shock absorbent for the electronics. The engineer matrix is the technique protective from and padding. The importantly for an adjustable leveling is flexible opening, and the important is trees. The next one, please. And the step 2 is the competitive benchmarking. We have two competitor. This is the concept A and concept B. About the opening level, opening time is 15 seconds. The concept A is 15 seconds and concept B is 5 seconds. And the number of transformation, we have the concept A is 2 steps and concept B is 1 step. The surface area is both when fully opening. Concept A account for 40% and concept B account for 100%. The thickness protected from concept A is the 1 to 10 mm and concept B is 0 mm. And the final is the range of opening angle. 90% to 180 degrees. Next one, please.
And to continue, this is the section target value based on based on oftentimes we are setting this is the smallest 5 seconds, and the second this is the number of transformation step we write to ideal value. This is the 1 step, and about the percentage of surface area is exposed when fully open. We set the ideal value. This is the 100%, and for the thickness to rotate still laptop and electronic device, we set the ideal value. This is um, thicker 12 millimeter, and as about the range of opening angle, we set the ideal value. This is from 0 to 180 degree. Please next. And after we set the standard specification, we continue to the concept generation. The first step is create the functional decomposition, and the first this is adjust the opening and closing capacity of the pack part to optimize the item asset and packaging speed. We set to for functional. This is the fast, accessibility, rotative, adjustable, and with the fast we separate it to the transform geometric step to from 2D to 3D and minimize open close cycle time. About uh, accessible, we separate it to the maximize field of view and represent the item displacement. And for the rotative, this is the circular top position and absorb mechanical shock. About the adjustable, we separate this is enable vary opening amplitude and adapt to any user device switch nestly. And based on the function documentation, we find some technical contradiction. The first contradiction, this is if we apply an external manual peeling force to transform from the last 3D 6 into the 3D backpack carrier, and then the system can train instead quickly, but it cannot snore. It accept final condition and failing to differentiate with the pack should become the pack or the postdom or the shyward of the pack, resulting this is the structural lab. So we use the twist matrix with the improved parameter if the durability of the moving object and worsening parameter is the stability of object composition. And then we find the inventive principle 10 preliminary action. This with ISB, I think with three Tracy. The first is yield original shape, and the second is use zipper, and the third is the management frog to make the material can know where will condition when they transform from 2D to 3D. The Nestle. And the second contradiction, this is if we use a uniform short material to ensure the origami free line can form smoothly and achieve the 3D step, then the transformation speed and step accuracy are perfectly smooth. But the panel temperature too sharp to rotate the laptop, completely failing to satisfy the rotative specification. So I use the improved parameter did it trail set and the worsening parameter is the trend, and I find the ISP 4C did it come portrait material. And with this idea I will use the form for the laptop protection position, and the other material I also use the short material snakely. And with this, Tracy, I come to step 3. This is create the step combination table with the 3 solutions. The first solution I call this is the origami envelope. To transform the shape 2D to 3D, I will use the origami retractor, the structural step geometry, and for the laptop protection, I will use the short form. And the second solution, I call it the semantic stripper. For the transform the shape from 2D to 3D, I will use the rigid material panel fiber port structure, and I also use the short form for the rotate laptop position. And the third solution, I call it the concatenate font. I use the Chinese sidewalk panel to transform the shape, and also use the short form for the laptop position. And Nestle, with this straight, no, yes. With this Tracy, I created some possible concept, and you can see in the imagery, this is 10 to 20 minutes to create the picture for everyone to imagine our concept. The first concept, we use the flexible cell with the origami structure, and we will fix it with the metallic slab. And the second concept, we use the zipper to fix the 3D structure. And the third concept, we use the origami and also the zipper to fix the structure. With the possible concept, we continue come to the cloning step. Nestle.
About the concept idea, um, about the concept idea, the concept A, the design allow the backpack to expand 100% of the flat surface. The outstanding advantage is the optimize the visibility of the item, far through the solving the problem and finding furniture in the traditional backpack. The concept B is the focus on high customized through the replaceable storage place. However, the option has a potential risk and the term of production cost and the complex inability in marking robotize. And the concept C is using the slide storage layer to access the item in a clear route. However, this design raised the concern about the weight and the mechanical strength of the sliding system. Next, please. Next one is the concept, the criteria and scoring scale to ensure the objectivity in the selection. We have the 6 criteria here. The first one is the transition speed. It account for 25%. Item visibility account for 20%. Organizability account for 20%. Rotation account 15%. Manufacturing 10%, and cost control 10%. Next, please. The evaluation criteria are like allocate on based on how important is the ORIPAC user experience and transition speed and item visibility account is the most important. So when the result of quantitative analysis so that the concept A achieved the highest total weight score with the 4.45. So our team decided to choose the concept A as the foundation of product development. Next, please.
Sorry, time is up.
Okay, the last part is it's okay. Just assess whether the technical specification meet our target or not.
So this is your conclusion of your final specifications, right?
Not yet, Professor. We use the HOKey to check whether we have missing details for the final specification. Cyan, we can skip to the end page. So this is the final specification, Professor. But we have maybe another plan we can generate for another concept from the HOKey.
Okay. I will look into that after you submit your transparency. So, any other question? As before, the group. This is group number 4 presentation. I think group number 3, you should ask question. Group number 3. Okay, I will ask one question first. Please go to the contradiction analysis, the inventive principle you identified. Go back. Okay, go back. The first one, the first contradiction. Okay, this one. Can you explain more about, so the inventive principle number 10, preliminary action, is the way you solve this problem. Can you explain more about how you apply this principle in your design?
As for the preliminary action, this means that we need some previous action to before our real action. And our problem this is because the material cannot know extract the position when they because they transfer from 2D to 3D. So I think I will set some I call this the remember line for the material when they transform, they can come to the exact position, and this I call this the preliminary action.
Because if you put do such technical contradiction, I think you should come up with some solutions. But because you show us 3 different
Yes.
methods, but
Yes.
because so that's why I need to know which one is better for the preliminary action. Because I can maybe all origami shape has
Yes.
some sort of preliminary actions, but zipper and the magnetic force, I can see they can apply in this kind of inventive principle, right?
Yeah. Yes, in my
So
position, I think origami set this is the space, and the second this is the zipper and magnetic.
Okay. Group number 3, have you have question for them?陈浩翔、庄子毅、詹子毅、陈湘云。You guys should ask question. Okay, maybe you will, group number 3 will ask question for the next group. Okay, let's continue. Group number 5.
Okay, thank you, Professor and everyone. We are from Group 5. And we will explain about our project progress. And we are with a member of Kenny, Calvin, Linton, and Aaron. Next. Okay, for the project overviews, this is our concept generation. I will explain it as mentioned, and product design will explain by Kenny, and specifications by Aaron, and contradiction analysis by Calvin. And next. And in this part, I will explain our concept generations and our project idea. Our product idea is an impact detector for the package delivery. And the goal is simple. We want to show if the package has been received a strong impact or during shipments. And so this product is not only give the warning labels, but it give the visual evidence when the package is drop or hit. And for the problems, opportunity, and concept targets, the main problem is that the fragile labels only warn people, and they tell handlers to be careful, but they do not show if the package was actually dropped or hit. And sometimes the box still looks fine outside, but the product inside may already been damaged. So our product is to create a simple and affordable impact indicator. And our target is to make the passive device that give the permanent visual evidence after the strong impacts. And this can help the seller, customer, and logistic companies during the damage checking or claim discussion. Next. And for our function diagrams, this slide show the basic functions of our impact detector. And the main function is to detect the strong impact and show the permanent visual evidence. And there are 3 inputs, the shock energy, the package movement, and the impact event. And for the shock energies, happens when the package is dropped or hit. And the package movement means the detector move together with the package. And the impact events mean the movement when the package receives the strong force. And after that, the detector sends the impacts. Then it compares with the impact with the threshold. And if the impact is still normal, the indicator will not be active. But if the impact is too strong, the mechanism will be active. Then the indicator will change the color permanently. So the output is the clear visual signals that show the package may have received the expected impacts. And next. And for the external research, we look at the several sources. First, we look at the users, such as an online seller, the small medium enterprise that often ship fragile products, and they need the better proof when delivery damage happens. And second, we compare the existing solutions, such as fragile labels, the indicator, the small impact indicators, and the digital data logger. And we look at their cost, the usability, the strength, and the weakness. And third, we consider input from the logistic worker, packaging suppliers, and experienced shippers. And this is useful because they understand the real package handling problem during the delivery. And we also review the pattern during the literature to understand possible mechanism and technical background. So the external search will help us to make the concept more realistic, not based only on our own assumptions. And next. And for the competitor analysis, we compare to common solutions, fragile labels, and digital data loggers. Since this part were already explained before, I will only highlight the main points. And the fragile label are cheap, chips because it's all, but it only gives the warnings. And digital data loggers are useful, but they only but it's more complex and expensive. So our product is positioned between them. And next. And for the fragile labels, the advantage is they are cheap, simple, and easy to use. But the main weakness is they are do not detect the real impact. And they also do not provide proof when the package drop or hit. So our product improve this by giving the visual result after the strong impact. Next. And for the impact recorder, they are more advanced because they can record shock during the transportations. But they are useful, and they also useful for the professional and high value shipments. But for the normal shippings, they may be too expensive and less practical. So our product focus on simple and more affordable solutions. Next. And for this slide, summarize the market gaps. And the fragile label are affordable, but only give the advice. The digital loggers give the more information, but they are too expensive and complex. So the market needs the solutions that give the clear evidence that the fragile labels, but still keep the simplicity of the sticker. That is the gap we want to fill. Next. And for our mission statement, it's a passive and tamper-proof impact indicators. And the idea is evidence over the advice. We do not want to warn the peoples. We want to show the proof when the impact is happened. So overall, the product can help reduce losses from the hidden shipping damage. Next. And in the slides, we compare 3 possible concept directions. We divide the product into 4 main functions: impact sensing and activations, and visual output, and tamper-proof feature. For the concept A, we use glass ampoules, but it always active, give the red color change, and use the irreversible die. For the concept B, we use the spring triggers. It has the full tap activations, the color scale, and the point S5. And for the concept C, we use the mechanical impact sensors. It also used the impact release latch, a mechanical reflect, and the sealed irreversible locks. But after comparing these 3 concepts, our conclusion is concept B is the strongest directions. And the reason is because concept B is simple, low cost, better visual, and easy to use for the normal package delivery. And it's also practical for the online sellers and business because it's easy to use, and understand, and easy to apply, and suitable for daily shipping. And next.
Yeah.
It will continue again.
Okay. Yeah, good morning everyone, and good morning Professor. I'm Kenny. Now I'm gonna explain about the product design based on the previous systematic exploration did by Vincent. So based on the previous concept of A, B, and C, we choose concept B as our catalyst, and I generated this for design of and their activation based on concept B. The first one is using the spring trigger as the mechanism, and the next one is tap activation, the color change, and lastly, the void adhesive. So we're gonna go into the concept scoring. First, we're gonna define the criterion. And the most important criterion in this case is the durability, to see if the product is, in the worst case, will break easily with a lesser impact, or in the best case, it's protected layer, reducing the direct contact. And I think the ease of use is also important in designing a new product, is to see whether it requires a manual training or it's just a pick up and play. It can be used by everyone. The other thing is feasibility in the manufacturing of the new product, is whether it requires a new tech that doesn't exist yet, or we can build it by an off-shelf part.
And next, we're gonna do the ranking of importance. We're gonna define the durability as 100, and the next one is by a lower score using the swing weighting method. And now is the normalization. We're gonna divide the raw score of each score divided by the sum of all the raw scores. And it gives us the rounded weight in the right table. And then the next one is we're gonna use the rating as here is we give the relative performance description as well. With 5 is better, is the best than the others, and 1 is the worst. Now we're gonna go into the selection criteria with the concepts and the selection criteria as well. First, we will like to count for the design one, the spring trigger. We would like to think that the durability for the spring trigger is the best one. We give it 5, but because of the spring trigger mechanism, we give it 2 for the ease of use, therefore giving a total score of 3.5. And the next one is the tap activation. For this one is all relatively in the middle of the rating, but for the uniqueness is we give, for the durability, we give it 3, is the highest score between the 5 selection criteria for design 2, and we give it a total score of 2.81. And the design 3 is the color change. This by far comes the best with the durability with the weighted score of 1.3, and then the visibility of 0.95, and then the ease of use of 0.8, and it gives us a total score of 4.26. And the last one is the void adhesive, is we give it a score of 0.78 for the durability and 0.8 for the ease of use, giving us a total score of 3.56. And then for the ranking is design 3 by far the best choice for our continuing development.
Okay, now the specification. Next slide, please.
Time is
The
up.
Okay, the specification is from the customer needs, so we do the depth interview. Next slide. Next slide, please. This is the customer need that we got, and then this is the technical requirement that we make, and then the next slide is the house of quality. Next slide, please. This is the house of quality. So we collect from the customer importance and from the metrics that we set up that we got from the customer need. And then this is the sum product, the relative weight, and the rank from the bottom. You can see the rank. The first rank is the 12, the matrix of the number 12. And then we can see like the next slide, please. We can see the rank of the matrix. It's like the simple visual instruction is the relative weight is like the very high. So like yeah, we try to make it later the product to make it to more into this matrix. So like we focus on this rank up from the highest matrix until the lowest matrix. Next slide.
So this is the contradiction analysis. Next. We have the 9 windows to see the blind spot for the future stages. Next. And this is the IR concept that we analyze. Since we have the zero cost, we analyze the gap between the reality and our IR to define the core engineering needs. So here we have the passive detections, tamper-proof evidence, automations, and also high economic viability. Next. And this is our technical contradictions. So moving into our design phase, our primary technical contradictions was balancing the sensitivity and reliability. So if we make the sensor sensitive enough to catch Lb drops, standard flux vibrations might cause false positives. We resolve this trade-off using the two-trees principle, which is the parameter change for trees number 35 and another dimensions for trees number 17. Next. And this is our physical contradictions. So we finally, our indicator phase of physical contradictions is it must be fragile to do its jobs, but strong to survive the handlers. So we use we using the separations in space. So isolate the fragile glass inside our dome, and also the separation in conditions. So ensure the mechanism is only yield in certain area. So we have first is whether the indicator is fragile, breakable, and also the indicator is strong. And the second question is when do I want the indicator to break or trigger, and also when do I want the indicator mechanism to perfectly intact. That's all for our presentation. Thank you.
Okay, because the time is limited. So just one question from, I think, group number 4.
So I would like to ask on the slide 2021 with a technical requirement. So I would like to ask, how will you decide the impact threshold? For example, 25G, 50G, or 75G?
Yeah. So the impact activation threshold, this one, the indicator, it depends on the product. If like the product is like very easy to fragile, so we will make it into very low of G. But if like the product is like very big or like I give an example, it's more easy. If like the product is like glass or like a bottle that with like a glass, from the glass, it will be make more lower G because it's like it's easy to break. But like if like the product is like some kind of metal, something like that, so we will make the impact activation threshold is like more higher because it will be depend on the product. It will be the same, but it's still our thinking also like because we still not design the product, so we still develop our thinking about the impact activation threshold.
Okay, thank you.
Okay, because time's up, so we will go to the group number 6. But however, I think you guys, before your presentation, you should rehearse your presentation and control your time. Okay, but however, I will look into your slide after the presentation. Okay. Group number 6.
Good morning, Professor and everyone. Today, our group will be presenting our project on designing and developing a shoe rack. So, the main goal of our project is to create a practical, efficient, and user-friendly shoe rack that solves common problem like space management and the organization. So, in this presentation, we will walk you through our entire process, starting from how we generated our idea, how we selected the concept, and what specifications we did, like we decided for our project. In this part of our presentation, I will explain how we generated the concept of our shoe drying rack. We did not directly start by saying, let's make a rack. Like first we understood the actual problem, divided and decided and then divided the problem into smaller functions, search for possible ideas, and then finally selected the most practical combination. So what we did in the concept generation. So in this slide, we are showing the three main steps we followed in the concept generation. First, we used problem decomposition. Like this means that we divided the shoe drying problem into smaller functions, so it becomes easier to understand what the product should do. And then secondly, we used internal and the external search. Internal search means ideas from our own group brainstorms, and the external search means we studied existing drying products and learn useful features from them. And then third one, the systematic exploration, like we combined different technical options in an organized way and selected the most realistic concept. And in this, we started with the main problem, the wet shoe after rain. Wet shoes dry slowly and they can create bad smell, and then they also need space for drying. So the problem divided into the six smaller functions. First, the rack should hold the shoe properly. The shoe should stay open and the stable during drying. Secondly, it should remove moisture. The water should either drain out or evaporate faster than normal drying. Third, the move air inside a shoe. Like this, like this is important because drying only the outside is not enough. Air should reach inside the shoe, especially like the toe area. And the fourth, it should control the smell and the hygiene. Since wet shoes can create bad odor, then the design should reduce damp smell and then can be easy to clean. And then the fifth one, it should be safe for daily use, and the temperature should be mild, and like the product should have basic safety production. And the sixth one, the space, like many people live in small rooms or the apartment, so the rack should be like compact. So this is the function diagram. In this, um, like at this stage, we are not focusing on the final shape of the product. Like we are only focusing on what the problem should do, like what the our product should do. Like on the, we can say on the input side, we have wet shoe, electricity or air, user action, and the water droplets. And in the middle, um, of course, we have the shoe drying rack. This is shown like a black box because we are focusing on the only function, not the detailed design. And then on the output side, we expect dryer shoe, moist air, collected water, and the safe top signal. So simply the wet to enter the system, air and the mild heat help to remove moisture, and then the water is collected. So this is the final result. Like is final result like is the shoe is going to dry or not. So this diagram helps us clearly understand the input and the output of our product. The internal and search and the external search. On the left side, internal search means ideas from our group brainstorm. Like we thought of using angled support so the shoes stay open. Uh, we also thought like placing a fan at the bottom to push air upward. So we added the idea of removable tray for dripping water. So we also considered making the rack foldable or for small rooms, and adding a timer and the overheat protection for safety. And then on the right side, external search means like, for example, if electric boot dryer use warm air directly inside the footwear, then the dish rack use drainage rack and the inclined position. So like So the shoe cabinet help with the order control and the organized store. Here we divided the product into four main parts: shoe support, drying action, moisture handling, and the control or the safety. So for shoe support, we compared vertical pegs, angled arms, mesh shelf, and the foldable frames. Like we selected angle arms because they are keep like they can keep the shoe open properly and can allow the air to enter inside the shoe. And then for drying action, we compared fan airflow, moisture absorbing pack, and we selected the mild warm air, like because normal air drying is slow and very hot air may damage shoe. So mild warm air is the safer and the faster option. And for moisture handle, we compared the removable drip tray because dripping water can collect in one place and then the user can remove and clean it easily. And for control and safety, we selected a timer and the temperature cutoff because the timer control the drying time, and the temperature cutoff protects the product and the overheating. So from this table, our selected concept is like angled arm for support, mild warm air for drying, removable tray for water collection, and then the timer and the temperature cutoff for the safe use. And so overall, our concept generation process started from understanding the real user problem. Then we divided the problem into smaller functions, search for ideas from our group and existing products, and then finally used a concept combination level and to select the best practical solution. This actually helped us to create like a concept that is simple, which will be simple to understand ourselves, which will be the compact, safe, and easy to clean, and then useful for the daily shoe drying.
So on the next part, we focused on the product design. So in this part selection, we conducted not only to choose like the project topic, but we identified the most flexible and suitable way for customers to use for the shoe rack. So with the selection criteria, we had like the concept screening and refining, and then we had to do with the engineering flexibility and evaluating what we are going to doing, and customer orientation, whereby we want to know what we actually want, because this product, it's basically for mostly suitable for people living in small apartments. And then we did the weighing concept scoring. And then the main evaluated criteria was that with the drying efficiency, easy to use, portability, that it can be able to be carried easily, and the amount of consumption of electricity that is used, because we want something that can save electricity. And this is also there for hygiene improvements, and also it should be cheaper because our target market, it's mostly people that are not financially stable in that manner. And why we chose it, it is faster for drying performance, better air flowage, and low energy consumption. And also, Savannah, please open the next one. Thank you. So this is like the proposed design concepts that we had. We first looked at the traditional shoe rack, and then we had the electric shoe rack that is basically there in the markets now, but it's a little bit expensive. And then we had our foldable shoe rack, and then we have the shoe drying rack with storage. And then on this part, we had the concept screening, whereby we were trying to gather the best one that we can use. So with the foldable shoe drying rack, it was the best of option because it's able to save time and space as well. Because we were considering that it should be something that could be able to be folded in order to save space in our places that we lived in. And Savannah, please open the next one. 10 minutes. Yeah. And then this is like the concept screening that we had over here. And we were able to grade it in its criteria. Please open the next one for the final one, Savannah. And the most suitable one, it was the foldable one, which had the highest score. And we ranked it number 1, which is the foldable and high drying efficiency. And it also has low consumption and better airflow. Next one.
Okay,
Maya.
so this slide presents the customer needs. So the most important needs are the fast drying and hygiene improvement and safe daily use and the good performance in humid weather. So customers also want low power consumptions, quiet operations and easy maintenance. Next slide, please. So this slide presents metric and values like customer needs are converted into measurable engineering metrics. For example, like fast drying becomes drying time, low energy use becomes like power consumption, and quiet operation becomes the noise levels. So this helps us to evaluate the design technically. Next slide, please. This slide combines the customer needs with the engineering metrics and the final target specification. So our targets are drying time less than 3 hours and the power consumption below 20 watts and noise level below 40 decibels and the airflow speed above like 1.5 meter per second. So the rack is also lightweight and easy to clean and designed for one pair of shoes. Next slide, please. So this slide shows the house of quality analysis, like it connects customer requirements within engineering characteristics such as airflow speed, drying time, power consumption, weight, and the cleaning time. So the relationship value for here we can see like 9 for strong, 3 for medium, and the 1 for weak relationship. So and the final weighting values help identify the most important technical parameter from this analysis like airflow speed, drying time, and the power consumption are the key engineering priorities for our design. Next slide, please.
Time's up.
So here is final product specification. The drying time target is less than 3 hours. Airflow speed should be above 1.5 meters per second. Power consumption should be remain below 20 watts. Noise level should be stay below 40 decibels. So the product weight is below 2 kilograms and support one pair of shoes for daily indoor use. Next slide, please.
Yeah, and then this is the concept design of our shoe drying rack. And I'm just gonna skip a few slide. Next slide. And we try to list for the technical contradiction, we use classic matrix and we try to list the improving parameter and worsening parameter. As you can see in the slide, there are for improving parameter is of manufacturer, device complexity, and so on. And as you can see for the worsening parameter. The next slide. After discussing with our group, we found the contradiction statement. In short, is we want it simple, compact, and easy for apartment living, but it must dry shoes thoroughly without causing damage. Next slide. So the improving parameter we use is operation, and the worsening is reliability. Then when we use the classic matrix, there are 4 results for the inventive principle, and we choose number 17. Next slide. The reason we choose number 17 is it gives us an idea that we want the air flows upward from the bottom to the bottom and spreads evenly to the inner sides of the shoes, and then the air still comes from below, but the nozzle can be directed toward the 2 areas for more effective drying. Next slide. And but also we have a physical contradiction because the fan will we use is a small fan. So the air gonna be the air gonna be weak, but we want it to strong so it can dry fastly. So the physical contradiction here is airflow must be weak but strong at the same time. Next slide. And this is the question where must flow mass airflow be weak, and then when mass airflow when, and then what under what condition mass airflow be weak? Next question. After considering this three question, we decide, next slide. We decide that we found out that the solution is in separate in space, and then as you can see in the table, we choose the segmentation to divide one big outlet into many small ones, local quality, and then coping. By applying separation in space, the shoe dryer replaces one large outlet with multiple small holes, distributing airflow to all parts of the shoe and achieving fast drying with a small fan. Thank you. That's our presentation.
Okay, so one question from group number 5.
Yeah, can I see your house of quality? Yeah, you can see there's some customer need on the customer need number 8 and number 9. In that customer need, you doesn't make some metrics for solve that problem, safe for daily use and attractive appearance. Do you mention why you doesn't solve that problem?
Because we only gonna use as you know the fun the fun for laptop, the small one. So that's why we're not solve the problem, because we are not using heater, so it's not gonna be spark any fire because of that.
But because it's electrical, so I think you still need to do the metrics for the safe for daily use, because it's not, then no one will be used. And then I also see some, I don't know, is it I'm the one that's wrong or no, but I see in your metrics it's like the can you previous slide? Can you open the previous slide? Yeah, this one, support one pair securely, like shoe capacity is one pair, but in your design product, I see it's like more than one shoe.
Yeah. I'm sorry, we tried to generate it with AI, but I don't know why that's the design come out. It's my fault. It's we designed it for a shoe, for a pair of shoe.
Okay, thank you.
It's my bad. Sorry.
Okay, I think we will take a break for 10 minutes. Please come back about 10:20. Okay, 10:20. Okay, I think I will start the next presentation. So good number 7. Okay, you may start.
I think I share the screen. Can we start?
Yes, you may start.
Hello?
Yes, we hear
Oh.
your voice,
Oh,
but
okay.
not very clearly. Yeah.
Oh, okay. Interesting. Oh, Professor, can you see the screen of the PowerPoint?
Yeah, we can see the screen
Oh, okay.
of your transparency.
Oh, okay, okay. Our first presenter is not doing well. So, okay, good morning. This is our our project, Team 7 project. So our project handle Claim Pro, and then so these are my team members. I will go. So we have four part. One is the concept generation, concept selection, project specification, another contraction analysis. And this slide is from the midterm. We recap from that. So we have a 8 customer need. From that, we have a dot priority score, and then secondary, and then the lower priority, and then what is our target user. So, and then from this, and then we will now move to the progress report. So this is the concept generation approach. So we apply the 3 method concept generation framework from our lecture session 6. So method 1 is the problem decomposition using a functional diagram. Method 2 is internal and external search. So where we review 5 patent and then 3 competitor product, and then the hygiene literature from our midterm. So, and method 3 is the systematic exploration. So with a concept combination table. So, and then the next slide is the functional diagram. So in here we have a 2 levels. So level 1 is there is a input, and also there's a black box and output. So our input will be the user hand, and then draw handle, and standardizer, and user motion. So output is the standardize the hand, standardize the handle also, and then we use the liquid, and also the door is open. So level 2 is open the blood box into the sub function. So store standardizer, detect the user action and release the standardizer, and then deliver to handle, apply to handle, and claim between uses. So we grouped it into the 3 columns. So trigger, and then hand side delivery and surface side delivery. So which fit into the combination table in the next slide. So in the next slide, so we use a concept combination table. So we have a trigger mechanism, so and hand standardization and surface standardization. So and then we select the 4 parts from the table. So variant A, variant B, variant C, and then the variant D. So these 4 variant cover a range from purely mechanical to fully electronic. So and then the next speaker will continue the slide.
Thank you. In this table, we compare the 4 variants slide by slide across the trigger, handle delivery, and electronics parts and cost level and power source. For example, the balance speed is for pole spring and is use the dual pole motion to power the spring points, and about the 8 components we showing in the part in the bone table. And also we can show in this don't need any electronic. And next slide. And in the slide 8, we showing the methods that we use to scoring which one is more important in this for this item. So we use the average and Epinger's 2-stage methodologies. And step 1 is to find concept screening, which means to using the plus, 0, and minus against reference products. And the step 2 is to weight concept screen, the quantification screening on 1 to 5 sorts, then multiplied by criterions weight. And upon this, we can eliminate the weakness concepts and select the final concepts from the service several. And next page. And so we can see that for our reference, is a well-mounted handling sanitizer dispenser, the existing product people use today. And as we can see, the variance A scoring 5 plus and 0 minus, and variance B and D has positive non-scores, variance C scoring 4 minus. So based on the matrix, we drop the variance C and advent A, B, and D to weight scoring. So next page. For step 2, each of our 3 team members scoring the 3 remind variance independently using the weight scoring template. The 3 matrices showing in this slide. So the goals code in each matrix mark is that member high scoring variant. So we bring this all 3 matches together for the team review. Next page. Thank you. Then after the team review, we agreed on the final consensual matrix shown here. According the 7-way criterion, variance B reached the total score that we can see that's 4.00, ranking the first. The variant A and variant D also get this 3.030. And so that our team make a decision is to develop the variant B. As a page. And so our select consists the variance B, the polar activity spring. To the variance B is retrofit sleeves that fit over the existing door handle. The spring load sprung inside the sleeve is mechanically acted by the natural door pull motion. Two micronosis spring the fine means connected onto the user plane and the handling surface during the single port. No battery and no separated button are requirements. And the select connected, we can see that the scroll height is in the weight matrix. It adjusts the top 3 customer needs from the meter. It uses only magnetic operation with no electronics, and is used about 8 of the street parts, which the flexible for our student team. And next week, the speaker 3 will present our product sophistication and contradiction analysis.
No voice.
Waiting a second, he maybe has some problem on his phone.
Okay. So, thank you. For Q7, we define a 20 target specification. Each metric has a marginal minimum value and has an ideal target value. They are grouped into 6 categories: sensitization, performance, usability, psychogeometric durability, retrofit compatibility, and cost. To give a few example, thus per actual in to the hand is at least 0.3 millimeters ideally 0.5. Trigger pull force is at most 8 Newton, ideally 5. Total weight is under 250 grams. Manufacturing cost stays under 250 New Taiwan dollars. Each metric is measurable and traceable, either to a consumer need for the midterm or to the project goal. Okay, next one. So this metric links the 8 customers' need from our midterm to 20 engineering metrics. Rows are the customer needs, columns are the metrics. Each dot shows where a need is supported by a specific metrics. Every need is covered by at least one metric.
10 minutes.
So we also construct a full house of quality with 6 rooms. The gold column on the left is importance. The priority scores from our midterm customer vote ranging from 3 to 4.7. The body of the metric shows the relationship between needs and the 10 most differentiating metrics. The right side benchmarks our concept against 2 each solution: award dispersion and antimicrobial coating. The roof and the top identifies 3 engineering conflicts the 2 synergize. These conflicts lead directly to a truth contradiction analyzed on the next slide. For
4.1 technical construction. For following seasons, we apply technical contraction analysis. The problem, we need to strong spray pressure to sanitize the hand and the handle, and the light pull force so the device remains passive. These two requirements conflicts. The parameters to improve the force stability and power. The parameters that worsen the reliability, convenience of use, and adaptability. We look these pairs up in the standard 39 by 39 contradiction matrix. The matrix points out 4 intensive principles. Number 10, preliminary action. Number 15, dynamics. Number 19, predictive action. Number 35, parameter change. Our proposed solution combines principle 10 and 35. The doors closing motion recharge the spring, so the next user pulls are pretentious pump that need only about 3 newtons to release. Question 4.2, following season 5-6, we applied physical contradiction analysis using the 3 separation questions. The contradiction, the sanitized outlet must be open during use and closed between use to prevent leakage, drying, and contamination. Where open nozzle tip closed inside the reservoir. When open during the brief spray, closed for most of the day. If open above the pressure, their hold closed below it. The best fit is the separation by time, with separation by condition providing the automatic trigger. Our proposed solution is a spring-loaded duckbill check value at nozzle outlet. The spring keep it closed and rest. During the action, pump pressure exits the spray force and the value opens. When pressure drops, it closes automatically.
Hands up.
So that is our report.
Okay, question.
I want to ask about the target specification. Which specification category, design station, usability, physical fit, etc., poses the greatest challenge for manufacturability, and why?
Sorry, can you ask the question again?
Which specification category, like sanitation, usability, other physical fit,
Oh,
poses the greatest challenge for manufacturability, and why?
you mean why we do the 6th category?
This the sanitation performance, usability, and ergonomics, which one of these that poses the greatest challenge for manufacturability,
Oh, okay. So
and why?
oh, actually, like the bigger challenge will be I think the triggering boot point, because it can be malfunctioning because of the pressure and the user pressure force and everything. So that can be the biggest problem for it. Yeah.
Okay, thank you.
Okay, I think we will continue because the time is not enough, I think. So Let's go to the group number 1.
Right. Hello, everyone. We are Group 1, and this is our team member, and this is our content. Listen.
We first from problem from day life and came out with our idea. Snow is moving out smart seed and smart peel back. If discussion, we choose smart peel back because creating medicine is a common problem, especially for elderly people and chronic patients. It is also practical and stable for making a prototype. Next page. We review existing smart peel back and found that many already have remind and connection and caregiver monitoring. However, some are expensive, complex, or not elderly friendly. Therefore, our approach is to design a simple, low-cost, and easy-to-use smart peel back for home use. Next page. Our product is smart peel back for medication, remind intake confirmation, and medication recording. The goal is to help users take medicine on time and reduce mistakes. Our target is elderly people, chronic patients, and regular medication use. We focus on a simple, low-cost, and easy-to prototype design. Next page.
And based on the background review, we define our product as a smart pill box for medication reminder, intake confirmation, and medication status recording. The main goal is to help users take medicine on time and reduce missed doses. Our target users are elderly people, chronic patients, and regular medication users. And based on the project scope, we summarize 5 key customer needs: reminder, accuracy, ease of use, recording, and safety. The product should remind user at the correct time, help reduce missed or repeated doses, and be simple enough for elderly users. It should also record medication status and use clear compartments or labels to reduce medication mistakes. These need become the basis for our function decomposition and product specification.
Okay, the process begins with the medicine schedule and the user information. Users first store the medicine in different compartments and set the medication times. Then the system keeps tracking whether the scheduled medication time has arrived. If it is not time yet, the system continues monitoring. When it is time, the device gives an LED and a buzzer reminder. After the user takes the medicine, the user presses a button to confirm intake. The system may record the medication status in a future version. The record can also be used to notify caregivers or family members. This diagram helps us connect customer needs such as reminder, confirmation, and the recording to actual product functions. Next page. Next page. Okay, after defining the overall function flow, we further decomposed the smart PO bus into several main functions. Each function was converted into a design question, and then we generated possible design direction. For example, for medication storage, the design question is how user can clearly distinguish different medicines. Possible solutions include spirit, compartment, data labels, and color coding. For the reminder function, possible solutions include LED lights, browsers, or mobile notification. For instant confirmation, we consider button confirmation like LED sensor and weather sensors. With sensor, the decomposition is important because it helps us avoid jumping to one single solution too early. Instead, we explore several possible solutions for each subfunction. This option becomes the foundation for the concept combination table or on the next slide. Next page. This slide shows our concept combination table based on the function decomposition. We list several options for each subfunction, include reminder mention intake confirmation, recording method, safety design, user interface, and the power supply. The purpose of this table is to systematically generate different product concepts by recombining the option. For example, one concept may use a browser reminder button confirmation, manual recording, clear label, a physical button, and a battery power. Another concept may use LED reminder, local memory, spirit complement, and simple display. A more advanced concept may include Apple notification, weight sensor, Apple recorder, mobile Apple interface, and plug-in power. Therefore, this table is not the final design yet. It is a structural tool that helps us generate multiple concepts before selection. In the following slide, we will compare this generated concept through concept screen and scoring, and then choose the most suitable direction for the prototype. Next page.
Okay, we generate 4 different smart firebox concepts based on the concept combination table. Concept A focuses on a basic reminder function with a simple buzzer and LED-like system. Concept B combines reminder intake confirmation and a medication recording function. Concept C adds mobile application support and remote caregiver monitor. Concept D use sensor for automatic medication detection and confirmation. Next page. After generating the 4 concepts, we apply a concept screening metric to perform an initial comparison. In this stage, concept B was selected as a reference concept because it provides a moderate level of functionality without excessive complexity. And if the function is better than B, we put the plus mark, but it's worse than B, we using the minus. And after we make this table, we count the number of plus and minus, and the next score of function concept A is 1. The 4 plus and 3 minus, so its next score is 1. And concept C and D is -1. Next page. And concept scoring metric to conduct a more detailed evaluation. Unlike the screening metric, the scoring metric apply weight score to each criteria. This allows us to quantitatively compare the concept based on the importance of different design factors. In our evaluation, feasibility, prototype difficulty, and cost receive relatively higher weight because this project is prototype oriented and need to be completed within course constraint. Next page. Concept B achieved the highest total score among the 4 concepts. The main reason is that Concept B provides the best balance between functionality, usability, development feasibility, and the prototype cost. Next page.
And after concept screening and concept scoring, concept B was selected as our final design direction. The main reason is that concept B provides the best balance between functionality and feasibility. It includes the basic reminder function, button confirmation, and local medication record. Compared with app-based or sensor-based concepts, concept B is easier to prototype and has lower development complexity. For our refined design direction, we focus on LED or buzzer reminder, button confirmation, local medication record, and a simple user interface. App function and sensor confirmation are not removed completely. Instead, we consider them as future improvements. In this way, we can keep the current prototype simple, low cost, and practical, while still maintaining the core function user need.
10 minutes.
After selecting concept B, we translate the customer needs into measurable target specification for the reminder function. We set a reminder time arrow within plus or minus 1 minute so the product can remind user close to the correct medication time. And for ease of use, we set the operation step to 3 steps for fewer. This is important because many target users are elderly people, so the operation should be simple. For intake confirmation, we use button confirmation. And for recording, the product should keep at least 7 days or medication status. For safety, we use clear labels and separated compartments to reduce medication mistakes. And these slides explain our three contradiction analysis. We found 3 main contradictions in our smart PO box. The first one is confirmation accuracy versus product complexity. If we add sensors, the confirmation will be more accurate, but the device will become more complex. So we use button confirmation first and keep sensor as future improvement. The second one is medication safety versus ease of use. More safety mechanism can reduce medication mistakes, but complex larks may make the product harder for elderly user to operate. And the third one is function completeness versus prototype feasibility. App connection and automatic sensing can make the product smarter, but they also increase development difficulty.
We use the trust system operator and IFR to analyze the product direction. Traditional PO box only store medicine, while current smart PO box provide remind and record. In the future, they may include sensor app and caregiver monitoring or IFR is to help users take the right medicine at the right time with almost no extra effort. Next page. Based on truth, we refine our concepts for a current prototype. We focus on remind button confirmation and local recording because they are simple and feasible. For future development, we can add sensor app integration and caregiver notification to improve accuracy and support. Next page.
Hands up.
Group 7, ask question.
Can you go to the slide number 17? 17. So I saw here a customer need like improve medication and local. Okay, so in with this customer need, I think before I was thinking about to do this smart bill. So when I do the market research in the market, there is already a lot of many things that fill this all customer need and everything. So this is not a question. I think your team should think about what we can do different from that they are product, because I think already a lot of product with this smart bill in the market. Yeah, that's all. Thank you.
Thank you.
Any response?
Will improvement our function and find some new way to improve our product. Thank you.
Thank you.
I think I just give one comment for now. The way you use trees should be use the night window analysis first to find the functions of your product. And then when you go to the detailed design, apply problem solving techniques. That's how we use the trees method. However, I will give you detailed comment afterward. Okay, next group. Next group. Next.
Okay. Okay. Hello everyone. We are group 2. We're going to talk about the anti-kick outlet protector with power loss prevention. Next page. And this is our contents. Next page. Let's start. We're going to talk about the introduction. Let's start with the problem background and why this problem matters. As we all know, wall outlets are usually located near the ground. This makes plugs highly vulnerable to accidental impacts from feet, vacuum cleaners, or moving objects in our daily environment. We also look into the current limitation of existing solutions. Products currently on the market mainly focus on child safety, dust prevention, or cable organization. However, they all share one major flaw. They cannot effectively prevent accidental unplugging during active use. Next page. So what are the real-life consequences when the plug gets clicked? It leads to sudden power loss, which can cause severe data loss and equipment damage. Furthermore, it results in loose or broken plug, creating user frustration and hidden electronic safety risks. This brings us to our design opportunity. Based on these pain points, we identify a clear need for a new protective solution. We aim to design a product that can, first, actively absorb uh, accidental impacts, second, keep plugs securely connected, and finally, maintain normal daily usability without causing inconvenience. Next page. And next, we will talk about the concept generation. Next page. For the concept generation phase, we first decompose the problem using a function diagram. We treat our protector as a black box. The main input is the translational energy from an accidental kick. Our internal function must absorb and dissipate this energy and isolate the plug. The final output is ensuring the plug remains securely connected with continuous power. Next page. After decomposing the problem, we conduct an external search to review existing marketing solution and patents. First, looking at the market competitors. We found that standard stock cover only protect the outlet when it's not in use. Cable management box are too bulky and accidentally increase the chance of being kicked, while industrial locking plugs lack impact protection and sacrifice convenience. We also review related patterns. For example, pattern A is a safety cover, but it has weak impact resistance and crack easily and kick. Pattern B is a locking device that secure the plug, but because it has no crushing and impact force is transferred directly to the wall socket. Through this search, we identify a key gap. Correct design completely fail to provide impact observation and user convenience and simultaneously. Next page. Okay. Next, we use a concept combination table for semantic exploration. We broke down the product into three sub-functions: energy absorption, plug security, and wall attachment. By combining different solutions, we successfully generate three distinct design variants. Variant A use spring and a slide lock. Variant B is a polysilicon-based shell, and variant C utilize a magnetic detachment mechanism. Okay, next page.
I will explain how we select our final concept. Next page. We created 4 concepts by combining different energy absorption, plug securing, and or attachment methods. Concept A used microspring, a slider lock, and outlet screws. Concept B used a silicone short, friction fit, and 3M adhesive. Concept C used magnetic detachment, a clamp, and wall anchors. Concept D used a silicone short, a sliding lock, and outlet screws. Next page. Next, we use pure selection for initial screening. Concept B was used as the baseline. A plus means better, 0 means similar, and minus means worse. Concept C had the lowest score because it is harder to install and may damage the wall. So concept C was eliminated. Concept A, B, and D were kept for further scoring. Next page. Then we set 6 criteria and West because our main goal is to prevent accidental unplugging, impact absorption, and plug securing ability were given the highest West 0.25 each. Installation convenience and stability were also important, so each was given 0.15. Cost, manufacturability, and worst damage prevention were given 0.1 each. Next page. After that, we compare concept A, B, and D using the scoring table. After comparing the 3 concepts, we can clearly see that concept D has the highest score, 4.9. So we select concept D as our final concept. Next page. Our final concept is concept D, the silicone shore absorb impact. The slider lock keeps the plug connected. The outlet screws improve stable installation without doing extra holes. Next page. We select concept D because it has the best overall performance. It provides strong impact protection, prevents unplugging, is easy to install, and avoid wall damage. Overall, concept D gives the best balance between protection, plug security, installation convenience, and daily stability. Next.
Okay, now I'm talking about product specification. From real life scenarios, we have extracted 5 core customer needs. These needs cover both protection and user experience. On the protection side, we have omnidirectional protection to resist daily kicks or collisions, equipment safety to maintain a stable power supply, and damage prevention to reduce the risk of physical damage. On our experience side, we emphasize easy installation without the need for special tools, and zero interference in daily use to maintain a normal plugging and unplugging flow. These 5 pain points are the fundamental starting points for our product design. And since customer needs are often subjective, we must translate them into objectives, measurable engineering metrics for actual development. We established a one-to-one mapping, for example, translating preventing accidental unplugging into a quantified plug retention stability, and reducing collision damage to impact absorption. In addition, we measure installation and operational convenience through installation time and plugging convenience. We also include product size as a metric to avoid a box design that could actually increase the risk of collisions. Through this process, we successfully engineered the user expectations into actionable data.
10 minutes.
We established specific product specification based on this engineering matrix. For safety and protection, our absolute target is no unplugging under moderate size impact. The product must also have sufficient impact absorption and durability to protect the equipment from damage over the long term. As for user experience, we require the installation time to be less than 1 minute, allowing general users to install it effortlessly. Furthermore, there should be the minimal increase in insertion and removal force. Coupled with a compact wall-mounted structure, this ensures zero interference in daily use. And on this slide, we use the house of quality to validate of our design direction. Notice on the left, among the 5 major needs, 4 of them, including protection and zero interference, receive a maximum weight score of 5. This indicates that these are the pain points the market cares about the most, corresponding to the 3 black dots in the central matrix, which represent a strong relationship. We can clearly see that plug retention and impact absorption are the core metrics for satisfying safety and protection. This will be the top priority for our R&D resources.
covers the installation time and plugin convenience directly determine the quality of the user experience. Through this metric, we not only confirm the validity of our design, but also establish the optimal priority sequence for our future product development.
Okay, I will talking about the TRIC contradiction analysis. Next page. Next page. And our goal is to improve plug's stability so the plug will not become loose when it is kicked or hit by objects. However, if we fix the plug too tightly, no more plugging and unplugging will become less convenient. So the key conflict is between plug stability and ease of use. We also need to consider other conflicts. For example, stronger protection may increase the product size, and stronger materials may increase cost and complexity. Therefore, our design is to balance protection, usability, and flexibility. Next page.
Hands out.
Our product needs to be strong and stable during accident impact, but it also needs to be easy to use during the normal operation. To solve this, we use two separations stretches. First, the separation in time protect the plug during impact, but allow easy use during normal operation. Second, separation in space. Reinforce only the impact prone area while keeping the user assist area open. Next page. First, segmentation. The protector can be divided into module parts for easier installation. Second, local quality. Only the impact prone area is reinforced instead of making the whole product bulky. Third, flexible shells and thin frames. Elastic materials can be used to be absorb impact force. Fourth, intermediary buffer layer is added between the external impact and the plug. Finally, another dimension, the structure can redirect the impact force away from the plug. Next page. This design includes an other protective shell and inside buffer layer, partial plug holding structure, and the open assist design. The other shell blocks direct impact. The electric buffer absorbs and displaces force. The partial holding structure reduces plugging losing without fully locking the plug. The open assist design keeps normal plugging and unplugging convenience. Therefore, our final design can reduce accidental power loss while maintaining safety, usability, and simple installation. Next page.
Okay, let's start with the finally current progress. Next page. And this is our complete milestones. And next page. And this is our design challenge and next step. Thank you for your listening.
Rule number 1, please ask question.
Hundred.
And what was the most important question when your team select the final concept?
We select our final concept through concept screening and concept scoring. The main criteria were impact protection, power loss prevention, is for use, installation convenience, manufacturability and the cost.
Okay.
After comparison, the hybrid buffer can design had the best balance. It can absorb impact, reduce plug losing, and still keep normal plugging and unplugging convenience. That is why we selected it as our final concept.
Okay, thank you.
Okay, and I think your contradiction analysis is kind of strange. It doesn't make it's kind of strange, I think, because I cannot see clearly in your slide. However, review the contradiction analysis after today's presentation. Okay.
Okay, sir.
Let's take a 5 minutes break. Then we will go to the final presentation. Okay, let's continue for the final presentation from group 3.
Okay. Hello everyone. We are group 3. Today I will present the consent germination phase for product make check. As you can see on the timeline, our team adopted a system's three steps methodology. First, in the problem decomposition stage, we utilize a black box model to clearly define the engineering inputs, the system itself, and the expected output. Next, through benchmarking and insights, we identified critical market gaps. We found that traditional cable clips restrict movement and cause stress damage over time. On the other hand, Velcro straps require cutting to adjust, which completely fails to meet the needs of the dynamic minimalist workflows. This analysis led us to our third step, consent combination, where we systematically cards make different fixation, slide and cable clips mechanisms to find the most optimal solution. Let's move into the next lab. You can see our detailed consent combination tables. To avoid falling into a local ultimate design, we broke the product down into 3 core sub-functions: the track base guide, the cable attachment, and the DEX mounting. We exhaustively list 3 options for each function. After rigorous evaluation of technical feasibility and user demands, we successfully converse on the highlight path, option 2. Our final winning concepts combines a magnetic rail lattice secured by N52 neodymium rings and mounted using 3N VHP tapes as highlighted in the bottom blue banner. This specific combination balance
Wait a minute.
Hey.
Are you supposed to change your slide?
Slide?
Slide, yes. I think you have go to the.
Next slide is the other one.
Are you sure?
Yeah.
Okay, continue.
Okay. Next one.
你的画面没有动。
Shit. Wait. 有看到did you see my
Now you are at the second slide.
Still in the second slide?
Yeah.
Next page.
Sorry. Do you see my slide now?
Okay.
Yes.
Yes, thank you. Sorry.
Hello everyone. Next, I will report on how our team selected the better concept in the first stage of concept screening. We apply the punch method using the traditional fixed cable clip as our baseline solution. We conduct a preliminary evaluation of the 4 initial concepts across 6 key criteria, including installation convenience, adjustment, visibility, and visual neatness. The results show that the net score of concept A, C, and D were -1 and 0. In contrast, concept B, the magnetic slide rail based, achieving 5 positive points, researching a net score of +4 and ranking first, although its manufacturing cost is slightly higher due to magnetic component. Its performance is a judgment, visibility, and unit visual order completely outperforms the other option. Therefore, we decide to eliminate concepts A and C, return concept D after revision, and choose concept B as our top concept to officially develop into Megatrack. Next page. After shortening the promotion option, we move into the second stage, concept scoring, to ensure the product personally addressing the score pain point of the user. We utilize the wedge score formula learning in class. We define score from 1 to 5 as very poor to excellent and assign wedge based on market research, where visual tightness receives the high wedge of 30%, followed by a judgment visibility is 25%. We conduct a detailed quantity comparison between concept B magnetic light rail and the received concept D rail slot. In terms of the most critical visual tightness and judgment visibility, concept B received perfect score of 5, contributing 1.50 and 1.25 to the wedge score. Although concept B only scored a 3 in production cost control, the final total wedge score research 4.45, significantly leading concept D score of 3. Based on the objective scientific data, we decide to eliminate concept D and efficiently select concept B as our final project topic. Next one. Next page.
So next, I'm going to about our product specification, and this is our link metrics to meet. So for the customer need, first, cable security stay in place mapped to the matrix 1, 4, and 5. Strong magnetic force locked in the clip while high excessive strength stabilize the base on the decks. Sourcing this premium component directly impact our unit cost. And next, for fixable movement with user action connect to matrix 1, 2, 3, and 5. The magnetic force must hold the clip without locking it, and a low friction coefficient is vital for smoothing gliding. We achieve this with a lightweight part count of just 4 pieces. Through engineering, this precision is added to the unit cost. And next one is no damage or residue on desktop mapped to matrix 4, 5, and 8. So to avoid the residue, we use specialized tape with clean removal adhesive strength plus a high stretch resistance base. Premium tape and protective material naturally drives up our unit cost. So the number 4 our customer need is scalable for various deck size, aligned with the matrix 1, 2, 3, and 5, and 7. For different deck size, interlocking segment provide modular expandability. Altering the total part count, the track joints affect the friction coefficient and require aligned magnetic force, while adding module increase material consumption and the unit cost. And fifth, the fast toll-free installation influence for matrix 2, 4, 5, and 6. Our toll-free setup relies on a low part count of the 4 pre-assembly parts and instant peel and stick adhesive strength. This convenience shift assembly to the factory, increasing assembly time and the most cost, which impact the unit's cost too. And number 6 is minimizing professional appearance target. Matrix 2, 5, and 8. A professional look means an eliminated extra path to keep a low part count, while an exterior needs high stretch resistance. Adapting specializing mating coating to element chip reflection increase the unit cost. So, and finally, the last one is to prevent cable from falling off the decks connect to matrix 1 and 4. To stop cable from falling, a strong magnetic force locks the clips onto the track, while the base relies on heavy-duty adhesive strands to stay mounted under the cable weight. Next page.
We use TRIZ contradiction analysis to explain how metric solve case design conflicts. This section is divided into two parts. First, we discuss the technical contradiction between fixed cable control and flexible movement. Then we expand a physical contradiction between a long road for use and a short road for packaging and shipping. So let's talk about textual contradiction first. For cable management products, the cable clip must hold the cables firmly to keep the desk clean and organized. However, if the clip is completely fixed and cable cannot move smoothly when the user pulls or adjusts it.
1 minute.
This may correct pulling stress, reduce usability, and invent damage cable over time. So solve these problems, we applied TRIZ principle numbers 15, dynamicity. Instead of using a traditional fixed cable holder, Matrix use magnetic clips that can sit along the road axis. This allows the cables to move with the user's action while still standing neatly arranged. Instead, dynamic styling turns cables fixable into fixable friction into fixable control balances neatness and usability. Next, we discuss the physical traditional of the roll base. For actual use, the rolls should be long enough to cover different desk layout and cable arrangement. However, from the perspective of back shipping and manufacturing, a long roll is not ideal because it increases product size, transportation cost, and production difficulty. To solve this contradiction, we use spatial separation and modularization instead of partitioning on one long fixed row. Matrix is designed as short interlocking row modules. During shipping, each module remains compact. During use, users can connect multiple modules to correct the left they need. On the other hand, modular rows solve the long short conflict enabling complex shipping and tailorable use. Next. Next. Thank you.
Question.
Okay, I have a question. How did the MagTech team apply tree theory to solve the technical contradiction where cable clips must hold cable firmly, but these clips reduce usability?
Okay. Wait, let me think. We use trees, principle 15 diversity. Instead of fixing the clips in one place, we design magnetic clips that can slide along a rail. This way, the cables stay perfectly neat, but you can still move them freely without any pulling stress. Thank you.
Okay, thank you.
Okay. Okay, that will be all for today's presentation. However, I will make some general comments for today's presentation. First, I think most of you have known at current stage, we are dealing with how to make the product design realized by using some sort of method, such as house of quality or the product specification, definition, etc. But from after this stage, you guys should continue improve your detailed design because we still have 2 sections left. That will teach you when you are dealing with product design, you should consider different form or consider for different purpose. Then you should improve your design based on that consideration. So that's the first comment. How I think you guys should know. And some of the second is the contradiction analysis. I think some of you may use it in the wrong way. But however, because for today's presentation, most of your slides use the small font size that I cannot see clearly. So I will spend some time to look in more details in your slides and give you some suggestion for individual groups. So I will finish this and in about 1 week, and then you can improve your product design based on my suggestions. And then in the final, I think in the final we will have the formal presentation. I will make some change in how to present your product design, your project. And then I will also give you some guidelines. And please follow this guideline to prepare your final presentation. But I will make some change how we proceed the final presentation. And the time will be at the final week, which is week 18. Okay, I think is there any other question so far? If you have question, you can come to my office hour. Come to my office and ask your question, or you can use line. But sometimes I won't see line very often. So sometimes I will reply a little late. So please ask your question earlier before your presentation. Any other question so far? If no, I would like to make a group photo. Please turn on your camera. Xinyu, please.
Okay.
Some of you still not clear, still not turn on your camera. Okay. Done? Are you done? 金宇
啊，
好了吗？
没有全部人开。
李义成、柯倩文、李佑善。
My camera is off. Sorry, Prof.
Okay, okay. All right.
3, 2, 1, go. Yeah. Okay.
Okay. I think I will make some change in your final presentation. Please read carefully about the guideline I provide. Okay. See you in the final presentation.
Thank you, teacher.
Okay. The TA
Professor.
state the rest of you can get off the line.
Okay, thank you, Professor.